Hello and welcome to our Wednesday webinar from the IEA Clean Coal Centre. My name is Benedicta and I'm the Communications Officer here. Our monthly webinars are based on our technical reports, which are available from our website www.iea-coal.org. Residents of member countries and employees of sponsoring organisations can download our reports at no charge after a one-off registration. The subject for today's webinar is CCUS status, barriers and potential, presented by Greg Kelsall. The report on this topic will be published very soon. Take it away, Greg.
Okay, thanks Benedict, and thanks everyone for joining the web today. The presentation will cover the case for CCUS. Sorry, we didn't click forwards then. We'll cover the case for CCUS, the status for CCUS globally, what lessons have been learned from the CCUS demonstration projects, the remaining barriers and opportunities for CCUS, and finally, I'll wrap up with some conclusions. So what's the need for CCUS? So looking firstly at this, the IEA Technology Perspectives report has assessed the required reduction in CO2 emissions to limit the global temperature rise this century to 2 degrees Celsius, the so-called 2DS scenario, and then to go beyond this to move towards an even lower temperature rise, the so-called better than 2 degrees scenario, or B2DS. These have been compared with a reference technology scenario, or RTS, which accounts for the current emission reduction commitments and is itself a major shift from business as usual. To achieve the 2DS scenario, it requires cumulative CO2 emissions to be reduced by 760 gigatons of CO2 by 2060, with 14% of this reduction, or a little over 100 gigatons of CO2, coming from CCUS. As you can see from the lower power plot, the power sector is a major contributor, accounting for more than half of this, representing over 50 gigatons of CO2 reductions. In terms of the B2DS scenario, this will require an additional 250 gigatons of CO2 emissions relative to the 2 degree scenario case, bringing the total required reduction to more than 1,000 gigatons of CO2, with CCUS providing 32% of this additional emissions reduction requirement. Looking specifically at what the IEA forecast would mean for coal, unabated coal for power plants would need to reduce significantly in both the 2DS and B2DS cases, from around 1760 gigawatts in 2020 to below 150 gigawatts beyond 2045. This would mean a reduction in unabated coal-related power generation of over 90%. A portion of the coal generation would be replaced by coal power plants fitted with CCUS, peaking at around 350 gigawatts for both the 2DS and the B2DS cases by around 2045. This could be new build power plant, including CCUS at the outset, or CCUS retrofits of existing coal-fired power plant. Interestingly, the capacity of coal with CCUS decreases little after 2045, as typical capture efficiencies of 85 to 95% still emit some CO2. So this means that CCUS is not consistent with a net zero emissions world without emissions offset from biomass CCS, or without moving closer to 100% CO2 capture. So where does CCUS stand right now? Unfortunately, CCUS is not currently on track to achieve the level of CO2 reductions required by either the 2DS or the B2DS scenarios. The IEA's Tracking Clean Energy Progress Indicator shows that only 7 of the technologies are assessed as being on track, and CCUS is not one of them. For CCUS, the 2DS trajectory indicates a 2025 target of more than 400 megatons of CO2 per year being stored by that date. However, the amount of CO2 captured and stored in 2019 was around 38 megatons of CO2, representing only 10% of that required 2025 level. And if the nationally determined contributions, or NDCs, of the countries party to the Paris Agreement are anything to go by, the signs are not encouraging. CCUS is largely absent from the NDCs. So this suggests that whilst the case for CCUS appears to be clear, this has not been carried forward in the policies of the majority of the nations. So having established the need for CCUS, this next section of the presentation looks at what is actually happening around the world. CCUS plays a relatively small role in power generation, with 2 operational power plants providing a combined 755 megawatts capability. Both are retrofits of coal-fired power plants located in North America, namely the 150 megawatt Boundary Dam CCUS facility in Canada and the 240 megawatt facility at Petra Nova in Texas, USA. These power plants continue to play a leading role in the total of 19 operational CCUS facilities globally. The majority of these facilities relate to natural gas processing applications, with the potential to store around 37 to 38 megatons of CO2 per year. In addition to these operational facilities, a further 4 are in construction, due to be completed by 2020 to 2021, with 10 in advanced development using a predominantly front-end engineering design approach, and a further 18 in early stages of development. The key regions in terms of CCUS installations are clearly North America, Europe, Middle East, and Asia Pacific. The Middle East is gas CCS focused, and Europe, whilst continuing to play a key role in cost reduction, is more focused on decarbonisation of industry and the production of carbon-free hydrogen. So I'll therefore focus a little more on North America and Asia Pacific region in the next few slides. So turning first to North America, 12 out of those 19 large-scale CCUS facilities are operating in North America. And as noted already, North America hosts both of the coal-fired power plant CCUS projects. This is due in large part to the income derived from the value of CO2 from enhanced oil recovery, supportive national frameworks, including the 45Q tax credit system in the USA, which I'll touch on later, accessible CO2 storage sites, and strong stakeholder support, including the private sector. An analysis of the 45Q tax credits has shown that it could spur retrofits of coal and natural gas power plants, with the potential to capture around 49 megatons of CO2 by 2030. So the region is therefore well placed to continue to play a leading role in the global rollout of CCUS. So looking at Boundary Dam and Petra Nova in a little more detail, both of these are retrofits of coal-fired power plant. The 115 megawatt Boundary Dam power plant in Canada was retrofitted with CO2 capture in 2014 and is rated at 1 megaton of CO2 per year capture. And the 240 megawatt unit at Petra Nova power plant in Texas started operation in January and is rated at, in January 2017, and is rated at 1.4 megatons of CO2 per year captured. There are similarities as well as differences between Boundary Dam and Petra Nova. Both plants use post-combustion solvent-based CO2 capture technology to remove 85 to 90% of the CO2 from the flue gas stream. Both systems use advanced amines to separate CO2 from the flue gas. Shell's CANSOLVE solvent at Boundary Dam and Mitsubishi's KS1 solvent at Petra Nova. The captured CO2 in both plants is used predominantly for EOR, with Boundary Dam selling the CO2 to a third party and Petra Nova having a financial arrangement whereby it shares in the income from the sale of oil from the CO2 captured. For the Boundary Dam project, one power plant unit was repowered to increase its efficiency prior to installing the CCUS facility, whereas Petra Nova was not repowered, and instead the capture system was retrofitted to a slipstream of flue gas from one of the existing units. At Boundary Dam, the main parasitic load for the CCUS facility's regeneration unit is supplied by low pressure steam diverted from the main power plant steam cycle, which leads to a derating of the steam turbine power output. Where in contrast, the regeneration energy for Petra Nova is supplied by a natural gas-fired cogeneration power plant, which produces 70 megawatts of net electrical power, around half of which is sold to the grid. Using steam for the power for the primary steam cycle, as at Boundary Dam, reduces the coal-fired power plant electrical output. Whereas on the other hand, using a dedicated combined cycle power plant to supply the regeneration energy increases the net power output of the station. However, this approach produces additional CO2 emissions from the combustion of the natural gas in the natural gas combined cycle, which is not abated. So the second area I want to look at is Asia Pacific, which accounts for more than 50% of global CO2 emissions, driven by the rapidly growing economies which rely on fossil fuels for power generation. Many countries, particularly those across Southeast Asia, have young fleets of fossil fuel power stations, with some 352 gigawatts of coal-fired power plants under construction or in planning. And in 2017, the Asia Pacific region was responsible for 72% of global coal consumption, with China alone contributing 48%. China leads the region's CCUS activities, with one large-scale facility in operation, 2 in construction, and 5 in early development. A previous comprehensive study of CCUS in China by the IEACCC concluded that China could realistically proceed to retrofit a significant portion of the country's coal fleet by 2035, provided that adequate policy incentives were introduced. However, more recent analysis indicates that China's CCUS policy is insufficient for further development of CCUS technology, citing lack of enforceable legal frameworks, insufficient information for the operation of projects, and weak market stimulus. So Boundary Dam and Petra Nova and the more recent FEED studies have all provided valuable learnings, which I'll briefly go through in the next slides. So the cost of CCUS is probably the single most important lever for the wide-scale rollout of their technology, and it has reduced significantly. Current carbon capture costs for coal-fired power plants with post-combustion CO2 capture using amine-based solvents are in the range of $105 per tonne of CO2 captured, as at Boundary Dam, to $65 per tonne of CO2 captured, as at Petra Nova. The Shan FEED study, which is based on a single 300 megawatt coal-fired power plant with 90% CO2 capture in Canada, as was the Boundary Dam plant, has a projected cost of CO2 capture which is 57% lower than the previously designed Boundary Dam facility. That is down to $45 per tonne of CO2 removed. A major contributing factor to this was the capital cost reduction, where the cost for the Shan facility is projected to be 67% lower than for Boundary Dam on a dollars per tonne CO2 basis, due to the reduction of the CO2 capture island cost, together with a lower level of power plant modification costs for the relatively more modern Shan power plant. Reduced variable operating costs and maintenance costs were also contributing factors for achieving this cost reduction. And the Chand feed study fits in a cluster of more recent project studies which fit at around $43 to $45 per tonne of CO2 removal cost, with a proposed timescale for commencement of plant operations by 2024 to 28. Further cost reductions for CCUS facilities through learning by doing will be achieved, where a learning rate of around 8 to 13% could reduce the cost for post-CO2 removal by a further 50 to 75% by 2060. Now, clearly there'll be regional variations in the cost of CCUS, depending on the local factors. And a study by Ferrari and others considered local specific economic factors to assess global locations for CCUS relative to base plant costs in the Netherlands. So considering total plant costs, China has the greatest cost reduction at around 35% less than the relative case in the Netherlands location, due to the significant savings in materials and construction labour costs. Indonesia and Eastern Europe were next lowest, with around a 20% cost reduction. And in terms of CO2 avoided, this cost correlates primarily with power plant costs. So it's not surprising that the lowest cost of CO2 avoided is in China, with a value of around 50 euros per tonne, with the highest costs in South Africa and Australia. Availability of this CCUS power plant was an issue in the early CCUS demonstrators, but it now appears to have reached acceptable levels. For example, the Boundary Dam CCUS facility faced technical challenges, particularly in the early years, including some process complications relating to fly ash and other contaminants, and there were significant levels of amine degradation. Major work has been undertaken to address these issues, including replacing some of the carbon steel infrastructure with stainless steel and the introduction of anti-fouling measures. And as a result, analysis presented by the Coal Industry Advisory Board indicates that the facility has now been able to achieve 85% availability levels since the end of 2017, when taking out those plant outages, which were outside the scope of the CCUS facility itself. And this compares with the design availability for CCUS facility of 85%, indicating that availability is now close to the design level. This is acceptable for a demonstration project, but availability will need to continue to improve to move towards power industry standards, where mature natural gas combined cycle power plants can now operate at availability levels in excess of 90%. CCUS based on post-CO2 capture typically aims at a 90% capture level. In the longer term, however, as near zero emissions power plants will need to be needed to contribute to a net zero CO2 future, higher capture efficiencies will be required. This is evident in the projections by the IEA I showed in the earlier slide 5, where coal power plants with CCUS start to fall away after 2045 due to their residual CO2 emissions. A study by Ferron and others in 2019 have shown that from a technical perspective, there is no limiting factor to the increase of capture rates from the usual 90% to higher levels. A fossil fuel power plant could be made effectively CO2 neutral by utilising intercooling in the CO2 absorption tower, for example. This, however, increases the capital cost of the CCUS facility due to the requirement for larger size absorbers and desorber columns, heat exchangers and CO2 compressors, as well as increased energy consumption. So for an ultra supercritical coal-fired plant, the efficiency reduces by around 1.5 percentage points to move from 90% to close to 100%. And the cost of CO2 capture increases by about 3.5%. Alternatively, the concept of co-firing a coal power plant with around 10% biomass and utilizing 90% CO2 capture levels to achieve near net zero CO2 emissions could also be an interesting solution. This would be particularly interesting as a relatively easy means of incorporating renewable electricity in countries with indigenous coal and forestry or agricultural waste materials. Increasing co-firing of biomass would potentially enable a fleet of CCUS co-firing coal-fired plant to move to negative CO2 emissions in the second half of the century. So this would give increased flexibility in the measures required to achieve a below 2 degrees C temperature rise target. Additional lessons learned from the CCUS demonstrators include the following. So scale up. As a general rule, power plants become cheaper at larger scale in terms of dollars per kilowatt output. The Boundary Dam 3 power plant at 110 megawatts size compares with the Shand feed study at 300 megawatt size. So an approximate doubling in size delivered a 57% cost reduction for the Shand project. And it should be noted that the size of the Sask Power's coal boilers in Canada is relatively small compared to modern coal power plants globally, where boilers are typically in excess of 660 megawatts or even over a gigawatt size. So this indicates that there's significant potential to reduce costs further through economies of scale. The layout of the CCUS facility is a key design feature to reduce plant footprint and therefore to minimize CCUS facility capital costs. The location of the capture facility in close proximity to the power island would reduce the length of interconnecting pipework, which would lead to reduced cost of materials, reduced complexity of facility integration, and therefore increased operating efficiency. Modular construction for major infrastructure projects has also been used successfully to drive down costs worldwide. So whilst such modularization is not always possible, the assembly of structural steel, piping, electrical instrumentation off-site has all been shown to increase productivity and to reduce travel costs and therefore to reduce construction times. In terms of efficiency, older coal-fired power plants have steam cycles with lower steam cycle pressure and temperature, often at subcritical conditions, with CO2 emissions typically in excess of 1,200 tons of CO2 per gigawatt hour, whereas modern advanced ultra supercritical coal plants can have emission rates as low as 670 tons of CO2 per gigawatt hour. There is therefore around a 1/3 reduction in emissions intensity between the older power plants and the more modern coal plants, which has a direct impact on the size of the CCUS plant and therefore a reduction in parasitic power losses and capital cost. Optimizing the envelope. So based on experience from Boundary Dam, for a nominally designed full load capture capacity of 90%, this capture rate can be exceeded when operating at part load, with over 96% capture being possible at 70-75% power plant load. So this would mean that a coal-fired power plant with CCUS could operate flexibly around renewable power generation with minimal impact on the overall near zero emissions targets. So this could be an interesting selling point for the role of coal power plants within an overall integrated energy system to deliver minimized emissions. Supply chain. So develop supply chains, increase competition, spur innovation and reduce technology costs, which in turn has a positive impact on capital cost. And operating cost reduction. So based on the experience at Boundary Dam and Petronova, the largest potential for operating cost reductions were in the areas of reduced amine degradation, key component, redundancy duplication, and system integration. So moving on now to the last section of my presentation. Despite the cost reductions that have been achieved to date, CCUS has been deployed in relatively few countries and in general has relied on the revenue stream from EOR. So whilst this has enabled the first wave of demonstration projects to get off the ground, policies currently in place are insufficient. More positive carbon price signals are needed to drive the growth in CCUS. Whether the carbon price is effectively valued through carbon emitted, emissions trading schemes, or tax credits on the amount of CO2 stored, the value needs to be around $40 to $80 per tonne of CO2 by around 2020, increasing to perhaps $50 to $100 per tonne of CO2 by 2030. Currently, less than 5% of global CO2 emissions have a carbon pricing regime which is consistent with this. Looking at carbon tax as the first example, this is directly linked to the level of CO2 emissions, providing certainty with regards to the marginal cost faced by emitters. It does not guarantee a maximum level of emission reductions, unlike emissions trading scheme. Norway introduced a carbon tax in 1991, which has proved to be successful in incentivizing the development of the Sleipner and Snøhvit CCUS projects. The cost of injecting and storing CO2 for the Sleipner project at $17 per tonne of CO2 was considerably less than the $50 per tonne of CO2 tax penalty levelled at the time for CO2 separated from natural gas and vented to the atmosphere. Carbon taxes have since been introduced in several countries, as shown here by the World Bank. Although there are typically exemptions for the different types of emitters, particularly those which participate in emissions trading schemes. These range from as low as $2 per tonne of CO2 in Mexico up to around $125 per tonne of CO2 in Sweden, although the tax in both of these regions is less than half of the greenhouse gas emissions for both countries. The carbon price is typically around $25 per tonne of CO2, which is where the Europeans emissions trading scheme typically sits. The second example is tax credits, as used in the USA, which have supplemented the revenues from EOR projects and have also provided an incentive for the geological storage of CO2. Known as 45Q tax credits, these seek to link directly the financial compensation to the amount of CO2 stored. This has been recognised as an enabler of the 6 large facilities in the USA that have come on stream since 2011, including Petronova. The tax credits can be used to reduce a company's tax liability, or if they have no tax liability, transferred to the company that disposes of the CO2 or traded on the tax equity. The tax credits have the benefit of being well established in the context of climate change mitigation in the USA, as they have been used to drive significant investment in renewables over the past 2 decades. Section 45Q underwent a major reform in 2018, so that now the tax credit increases linearly each year to a maximum of $50 per tonne of CO2 for saline aquifer-based geological storage, or $35 per tonne of CO2 for EOR by 2026, and tracking inflation thereafter. The key feature of this tax credit is that it is performance-based, in that it is only awarded when CO2 is captured and then stored in conformance with federal requirements. Similar tax credits are being considered in other countries, such as China, and a recent study has shown that CCUS costs are still high for coal power plants in China, and 45Q tax credit provisions could effectively improve the investment benefits for CCUS projects there. Shared transport and storage networks can improve the economics of CCUS due to economies of scale and overall de-risking of storage liability and cross-chain risk. Heavy industries often exist in clusters close to local resources, power generation supply, and port or rail infrastructure. These industrial clusters can be supported by providing CO2 transport and storage network infrastructure, which multiple CO2 sources can access. This reduces the unit cost of CCUS as the CO2 network capital cost is spread out across an increased quantity of CO2. And it also reduces the cross-chain risk by creating multiple customers for operators of the CO2 transport and injection business. This provides greater levels of operational flexibility than a single source and sink facility, and it reduces the operational risk. The initial investment in a hub and cluster model, however, could be a barrier unless guarantees are provided for revenue during the early stages of development. In the UK, for example, the regulated asset base has been used to enable private investment in infrastructure. These regulated asset bases utilise a legally binding licence with periodical regulatory review of long-term tariffs. In this setup, all investments made are valued and costs are recovered from consumers under regulation. So the consumers effectively cover the risks, which in turn shelters investors from exposure to them and facilitates their investment. The example I show here is an approach being used in the UK for the £170 million industrial decarbonisation competition funded by the UK government through Innovate UK. The ambition is to have at least one low emissions industrial cluster operational by 2030, which could then move to net zero by 2040. A number of clusters will be funded through to FEED study, with the largest in terms of CO2 emissions being the Humber cluster, anchored by Drax, the former 3.6 gigawatt coal-fired power plant. 4 of the 6 pulverised fuel boilers at Drax have already been converted to 100% biomass, and the cluster will include one of these boilers fitted with CCUS by 2027, with plans to add the remaining 3 boilers by 2035 to generate negative 16 megatons of CO2 per year. The perceived risk of CCUS projects is a key factor in determining the availability of debt and equity finance. Some of the key risks for CCUS projects are highlighted in this slide, which indicates that the risk premium for CCUS projects is currently around 11%. So when added to a standard low-risk project debt financing of around 4%, this will bring the debt rate for CCUS projects currently to around 14 to 15%. Although the numbers in this table are not absolute in terms of their impact on risk debt lending rates, it does show where the development and prioritisation of policies should be focused to give the greatest cost reduction. These risks should be reduced in order to lower the debt and lending rates for CCUS projects. So looking at the top risks, cross-chain risks, whilst the separation of capture, transport and storage elements of CCUS is considered to be the most likely model, it does introduce challenging cross-chain risks, where there is a chance that one party in the supply chain defaults on its obligation to supply or take CO2, affecting the other parties in the chain. A greater role of government in taking on the risks could alleviate this problem, or at least provide a clear structure to allocate risk between the various entities. Policy risk. So there's the potential for changes in political support, which pose a risk for any CCUS investment, which is directly dependent on government policy for its commercial viability. Changing incentives for renewables in some countries has damaged investor confidence in this sector, and investors may perceive an even greater risk for CCUS, where there has been a history of changing political support. And storage, liability and leakage risks. So whilst the risk of CO2 leakage from geological storage is low, the impact is a cost to the project which is difficult to quantify. So leakage risks could feasibly be covered by government as a recognition of the broader value of CCS to society. For capital-intensive projects such as CCUS facilities, the cost of debt and equity can have a significant impact on its financial viability. Banks have a critical role in providing debt finance, which must increase significantly in order to achieve the necessary growth in the number of CCUS projects. To qualify for debt financing, CCUS projects will need to provide insurance that the key risks are identified with mitigations in place and that hard to manage risks are allocated to government in the short term. This is because equity investors require higher rates of return on higher risk investment loans. The different sources of financial instruments are shown in the table here, noting that project financiers will typically utilize a range of financial instruments to reduce project risk exposure. Some of these institutions specialize in high risk environments, including in developing countries. So commercial debt, these are asset-backed loans that can be secured over the medium to long term and have historically been an important source of finance for both fossil and renewable energy projects. Green banks, so these are banks that specifically target green or low carbon investment with the advantage of providing deep liquidity, but the disadvantage that they are limited in scope and may not support CCUS and they are region specific. Investment insurance agency or export credit agencies. So these are government or private financial institutions that can offer financing to domestic company international operations, and they help to solve risks such as export and political risks of overseas investments. And finally, multilateral banks and international financial institutions. So these include multilateral development banks, which serve developing countries, and multilateral financial institutions which specialize in types of projects rather than regions. Overall, as CCUS industry matures, risk reduction will make lower cost finance more available, which in turn reduces the cost of investment. So in the longer term mature market stage, projects tend to comprise exclusively of equity and debt capital. One potential business model that incorporates the features I've described in this presentation has been proposed by the UK Cost Reduction Task Force. It proposes that CO2 capture related projects which generate electricity could be supported using the existing UK Contract for Difference mechanism, the CFD mechanism. For CCUS, CFDs could be awarded by the Secretary of State through bilateral negotiation rather than competitive auction. And in the future, the UK government should consider whether CFDs for CCUS projects could be awarded through a competitive process. The CFD strike price for CCUS would need to reflect the cost of CO2 capture and generation, as well as the relevant project's proportions of the CO2 transport and storage fee. However, the transport and storage fee could be a separate pass-through element of the overall revenues and not part of the CFD strike price. Additional features of this model are the separation of the transport and storage infrastructure, which the government-backed equity and debt fundraising could use a regulated asset-based model to achieve. Additional opportunities to support CCUS include governments. So governments could send a much stronger message on the value of CCUS by explicitly including it in their respective national climate strategies and nationally determined contributions for those countries parties to the Paris Agreement. System network operators could recognise the value of the auxiliary services, such as reactive power and frequency response provided by coal power plant fitted with CCUS, and allow for financial compensation for these services. Such facilities will become increasingly important as the share of non-dispatchable renewable power sources, primarily wind and solar, increases in global power systems. And the integration of a CCUS facility must therefore not adversely affect the power plant's ability to provide these services. A coordinated and extensive CO2 storage assessment program is required, particularly in countries with indigenous coal reserves, which, given the long lead times in developing CO2 storage, should start urgently. And CCUS champions or groupings of champions, such as investors and non-governmental organisations, need to be in place and active to provide complementary reasons for the need for CCUS across a spectrum of interests. This is because technical experts presenting the CCUS message to date have often been from coal and/or the oil and gas industry sector, who the public perceive as having a vested interest in perpetuating fossil fuel-based power generation in industry. So moving finally to my conclusions. Around 350 gigawatts of coal-fired power generation with CCUS will be needed by 2060 as part of the transition to a net zero CO2 emissions future. Asia Pacific, including China, will be a key region where this will need to be implemented. And this must be achieved as part of a combined approach of limiting global temperature rise, whilst providing access to reliable and affordable energy to support economic development and improve living standards. This forms part of an inclusive transition where OECD countries should work with developing nations to move towards a lower emissions future that does not disadvantage an important section of the global population. Good progress has been made in reducing the cost of CCUS through the early commercial scale demonstration projects and the latest front-end engineering design studies, with CO2 capture costs now projected to be in the range of $43 to $45 per tonne of CO2. And further cost reduction can be expected through learning by doing, where perhaps a further 50 or more percentage cut could be expected as the technology is rolled out commercially through to 2060. However, to kickstart this rollout, a strong financial and regulatory regime will need to be put in place, which delivers more positive carbon pricing signals, provides investment for carbon transport and storage infrastructure, and provides more accessible debt and equity financing on the back of lowering CCUS specific project costs. Okay, thank you to everyone for listening. I hope that was interesting. I'll just open up the questions and see if there's any questions which have been asked. I wonder if I can make these bigger. Is this need for CCUS not a need? Is this need for CCUS not a need for B biomass carbon capture utilization and storage. Coal CCUS is CO2 neutral and will not reduce CO2 emissions. It will neutralize. Okay, so I think we would need we'd need both. I think some areas will continue to use coal, and moving to applying CCUS to coal would enable those countries to continue to use indigenous coal reserves. And the closer we could get to 100% CO2 capture, the more neutral that would be. Biomass CCUS or BECCS would help to generate negative CO2 emissions and offset some of the more difficult CO2 emissions from other sectors, such as the industrial sector. And as I tried to indicate, it would introduce flexibility in the second half of the second half of this century, to help to deliver a 2 degree C temperature rise. At the moment, I'm not seeing any additional questions on my screen. I mean, clearly, if there are more questions anyone wants to ask me, I'm showing my email address here, and I'm very welcome to people contacting me. We'll also be issuing the report on this presentation in the next few weeks, so feel free to comment on that report and feedback to me that way as well. Okay, so if there are no further questions that I can see anyway, that concludes my presentation today, and thanks to everyone for joining. Thank you.
Thank you so much. The slides from this webinar will be available to download from the webinar page of our website shortly. And all there's left for me to say is that our next webinar will be on Wednesday, the 13th of May at 12 noon, as usual. It'll be on coal use in steel production and will be presented by Paul Barua. Thank you all for joining us today, and goodbye.